and good evening, everyone. Okay, I will start, of course, with a reminder that nuclear power systems have enabled tremendous strides in humankind's exploration of space. All these iconic missions that are illustrated here were made possible, were powered by nuclear energy, from Apollo lunar scientific experiment to New Horizon, the first spacecraft to have explored Pluto, or the car-size rovers, Perseverance and Ingenuity, which are exploring the crater of Mars, or Galileo, the first spacecraft to have orbited an outer planet, Jupiter, or Cassini, which orbited Saturn for 14 years and was the first spacecraft to land a probe on the moon of an outer planet, Titan. We heard that previously. And of course, the iconic mission Voyager 1 and 2, which after having explored Jupiter, Saturn, Uranus, and Neptune have now left the heliosphere and continue to send valuable data more than 45 years after their departure from the Earth. All these missions were made possible by nuclear energy, were powered by radioisotope thermoelectric generators. These are these thin cylinders which are shown on the picture. The principle of these RTGs is that the heat released by a radioisotope is converted into electricity by an array of thermocouples, and the waste heat is radiated into space. A typical RTG, such as the one which equipped New Horizon, has a mass of 56 kilos and supply around 300 watt electric at beginning of life. The reason for this key role of nuclear energy in this iconic mission is that there is no practical alternative to nuclear for powering missions aiming at exploring space region where sunlight is too weak. Indeed, in space, there are only two options, photovoltaics and nuclear, for supplying sufficient energy for an extended period of time. And we know that mass budgets are tight, being tight, and power sources tending to be the heaviest piece of equipment on any spacecraft. There is a strong incentive to adopt the technologies that offer the highest specific power, that is, the highest ratio of power to mass. Nuclear is, of course, well known for its intrinsically high specific power, and PV, the specific power of solar arrays depend on solar irradiance, which decreases at the square distance of the sun, which explain why RTGs, radioisotope thermoelectric generators, outperform solar panels plus battery when the distance of the sun is when the sun is too far away, that is essentially beyond Mars, or when the sun is eclipsed, like during the 14 days of night on the moon, or obscured for a long period, for instance, by dust storms on Mars. Well, RTGs have well served the full exploration era. They will continue to be quite valuable, but now new nuclear fission systems are new high energy density nuclear fission systems are needed to enable a new class of more ambitious space exploration missions that are being envisaged today for the coming decades. You have to keep in mind that current space-powered propulsion systems limit deep space robotic exploration. Just think of New Horizon that with its 300 watt electric RTG and chemical propulsion was only capable of a speedy flyby of Pluton and took over a year to transmit back to Earth what data it could collect. Just imagine what could have been learned if New Horizon had the propulsive capacity to orbit Pluton and the power capacity to supply more powerful instruments and data transmission system. But what is driving the new power systems and propulsion systems with higher performances is the opening of a new human space exploration era. We heard about the revolution space with great ambitions. The first human back on the moon surface around 2026 with sustainable lunar exploitation targeted by 2030, opening the way to Mars humans exploration of Mars around 2040, which requires so higher power and propulsion performance systems. Nuclear fission systems can enable the sustainable driven mission of this new area of the coming decades, things that we are considering permanent lunar outposts, relying to in-situ resource utilization, and more generally, extraction of local resources, which requires industrial-scale, robust and safe high-density energy sources, implying nuclear fission sources. And this new era of human exploration also bear challenges in terms of logistic and in-space transportation, requiring increased or advanced thrust-efficient space transportation systems or space propulsion solutions, which, once more, nuclear fission can offer. What do these systems look like? First, nuclear fission power sources, or it's essentially a nuclear microreactor with its radiation shield, the heat source, an energy conversion system, and a radiator to radiate waste heat into space. These fission systems could supply a few kilowatt electric to a few megawatt electric, independently of the sunlight, as compared to RTG, which are limited to a few hundred watt electric. And so this would enable a permanent outpost on the moon, in-situ resource utilization, and such nuclear fission power sources could power nuclear electric propulsion and spacecraft instrumentation. Nuclear propulsion is of two different types. First, nuclear thermal propulsion, where propellant, hydrogen, is heated up to high temperature by fission reaction in a nuclear reactor and then ejected through another at high velocity, compared to chemical propulsion, because the heating reaction doesn't require any oxidizer. Then you could use a propellant with a much lower density, thus which explains why you can get a thrust efficiency 2 or 3 times higher than already highly efficient cryogenic engines. And so it enables to consider or to offer lighter space transport or space transfer vehicles, or larger payload, or faster transit, in particular interest for Mars mission to human mission to Mars, where you are eager to reduce the exposure of the astronauts to harmful space radiation. The second type of nuclear propulsion is nuclear electric propulsion. The system is quite simple in the sense that it's just, in bracket, coupled electric thrusters that are powered by a nuclear fission power source. Compare nuclear thermal propulsion, it offers thrust efficiency 3 to 5 times higher, but at a much lower thrust. And in comparison with solar electric propulsion, it enables higher higher power output, so higher thrust level, and of course, the performance is independent of the solar irradiance. So it would enable, I would say, a new class of in-space exploration and in-space logistic on the Earth's orbit and beyond, on a scale that neither solar propulsion or solar electric propulsion nor chemical propulsion could ever provide. Okay, what is the status of these technologies? Let's start with nuclear fission power systems. Such systems which could be used to support permanent outposts on the moon could be developed within a decade. Indeed, such power systems are not new. For instance, the Soviet Union launched more than 30 space nuclear reactors of 3 kilowatt electric, which are shown here. And this dates back to the 1970s and 80s. And one decade later, the US developed the SP100, which is a system with a power of 100 kilowatt electric, which was, the program was stopped just before nuclear ground testing. What is the current, what are the current developments? They are essentially, as we know in the US, first with the development of kilopower, a system which is scalable from 1 to 10 kilowatt electric, and which was ground tested, the object of a nuclear ground test in 2018. And last year, the NASA awarded contracts for initial design development for a 40 kilowatt electric fission surface power system that could be ready to launch within a decade for a demonstration on the moon. So this was for nuclear fission power system. What about nuclear thermal propulsion? Well, to build a nuclear thermal propulsion engine doesn't require fundamental technological breakthrough, but to design and deliver such an engine will require not only really good engineering, but also sustained commitment and substantial investment over the next 2 decades. In the past, the US as well as the USSR have devoted huge development to this nuclear thermal propulsion technologies. The US Naval rover program achieved a TRL of 6, and the 3 experimental nuclear rocket engines, which were ground tested, are claimed to have demonstrated all the requirements for a viable lunar space transport system, as well as for human Mars exploration missions. The current development, once more, are essentially in the US, as we know, as we are aware of, with in particular Project Draco by the DARPA, the DoD agency, which is a project for demonstration rocket for agile cislunar operation, which target full-scale in-orbit demonstration in 2027. The NASA had awarded contracts previously, but has now decided to partner with DARPA on the Draco project. Now, nuclear electric propulsion, well, you could consider that there are nothing more than space fission power system coupled with electric thrusters, which is true. However, for space tech applications, cargo or manned mission to Mars, they too will require really good engineering and sustained commitment and substantial investment over the next 2 decades. Indeed, such application will require power level in the few megawatt electric range, meaning more than one order of magnitude beyond what has been developed in the past in the US, and the same for the electric thrusters. It will require clusters of electric thrusters in the 100 kilowatt electric range, once more one order of magnitude beyond demonstrated thrusters. Current developments are essentially in Russia and in China. In Russia initiated in 2010 the development of a 1 megawatt electric nuclear power space tug planned to be delivered in orbit by 2030, and Rosatom reiterated several times this objective to deploy the system in orbit in 2030. And last year, China disclosed that it was developing a 1 megawatt electric space nuclear reactor, in bracket, to help its mission to the Moon and Mars, but we understand that it is for nuclear electric propulsion. What about Europe? The High Scientific Council of the ENS addressed the question in a position paper that we released last year. First, Europe has historically been totally dependent on the US for missions requiring RTGs, and this has led to a self-limiting approach of the European scientific community to propose only non-nuclear solution, which has limited its capability or its ability to contribute to the exploration of the solar system, in particular beyond Jupiter. Things are changing. The ESA announced the launch in November last year of the ENDURE program, a program led by the UK, which is devoted to the development of European devices for using radioisotope powers. So it's the first step toward some independence in the medium term of Europe for RTG. But with the new human exploration era which is opening and which require increase in space power and propulsion performance, Europe needs to look beyond RTG. This has been recalled by previous speakers, but transportation and energy are two of the critical aspects of space exploration, and they are essential prerequisites for the generation of strategic benefits, let's say innovation, inspiration, or strategic economic capabilities, in particular for exploiting extraterrestrial resources. So for Europe to retain its leadership position in space exploration, it should position itself on the development of space nuclear fission power source and nuclear propulsion systems. Europe has everything at stake to meet the challenge. It has nuclear and space R&D and industrial capabilities. It has a long tradition of excellence and internal cooperation in each of these two fields. So by mobilizing its well-renowned space and nuclear communities, Europe can, to meet this challenge, Europe can take its rightful place in this endeavor alongside the main space powers. But this endeavor is a long-term endeavor, meaning that a sustained commitment of and sustainable initial investment by European institutions will be crucial, and therefore for this endeavor it is essential as a first step to build long-term European nuclear and space strategy which addresses both power, RTGs and fission systems and propulsion, of course, a strategy, a long-term strategy that be robust, resilient, and affordable. And my last slide would be to acknowledge the recent initiative or the recent launch. The contracts are being signed now by ESA on 2 feasibility studies dealing with nuclear propulsion, which will be managed by the Future Space Transportation System Department of ESA. One is on nuclear electric propulsion, Project Rock and Roll, and the other one is on nuclear thermal propulsion, Project Alumni. And so we can see these first 2 feasibility studies as a first step toward the elaboration of a roadmap on a European strategy for nuclear propulsion. And I should also mention that not at a European level, but UK also through its national agency has contracted industries for developing or for proposing the initial design of a surface fission power source for application on the moon. So thank you very much for listening. And for those who are interested in the position paper the European Nuclear Society High Scientific Council published, you have the link to download it. Thank you very much.